So finally, what I want to do to just conclude this week's section is I want to talk a bit about a special type of utility function, which is called the Cobb-Douglas utility function. In general, if there's only one thing that I want you to take away from today's section, it would be knowing how to derive, but most importantly, the general solution for a Cobb-Douglas utility function. It's a utility function that we'll see a lot in the course, and so it's really important that you both understand the logic of the solution, and then also you either memorize it or just remember the logic, and so you have the sort of general solution in the back of your head as you're going through and solving problems. It will save a lot of work. Even though we didn't mention it above when we were thinking about utility of apples and oranges, where apples, utility of apples and oranges was given by apples raised to the 2/3 and oranges raised to the 1/3, that was a Cobb-Douglas utility function. And so we're going to see a lot of it. With Cobb-Douglas utility, the optimal consumption bundles are always going to take a particular form, which means you don't need to always derive the full steps shown in exercise 1 to solve for the optimal consumption bundles. So let's cover the general solution now. So suppose that a consumer has utility over goods X and Y. We're going to be a little bit more general than just apples and oranges. And suppose that X is raised to the exponent alpha, and Y is raised to the exponent beta. The marginal rate of substitution here is the first thing that we want to figure out. So recall that the marginal rate of substitution is just going to be the marginal utility of X over the marginal utility of Y. And so what we can do here is, again, what we're doing is we're just figuring out in order to figure out the marginal utility of X, remember that we just take the partial derivative of U with respect to X. So here we pull down the alpha, that's the exponent in X. We take alpha and subtract 1, and then we just leave that Y beta alone for the partial derivative of U with respect to Y. We just pull down beta, subtract 1 from the exponent on Y, and just leave X over alpha the same. Okay, and then what do we do? Well, notice that if we have Y beta down here, then what we were doing implicitly is we're subtracting beta and adding 1. So we'll be left with Y up here. And then down here, what we're doing is essentially we're subtracting alpha from down here plus 1, so we get X down here, and then you can see that alpha and beta just remain as they are. So the MRS is alpha over beta, X over Y. Recall that the optimal rule was that the MRS is going to be equal to the price of good 1 over the price of good 2, or PX over PY. And so then the optimal consumption rule is going to be that alpha over beta X over Y is equal to PX over PY. Okay, so this is great. This gets us some part of the way there. But now what we want to do is we want to solve for X and Y alone. So what are we going to do? We're going to go back to the budget constraint. And so remember that the consumer's income is I here, and the consumer can consume both X and Y. So they're limited by their income, but they're going to have a amount of expenditures on X given by PX times the amount of X that they consume, and then PY times Y. So that's going to be total expenditures on Y, or the price of Y times the amount of Y that they consume. Okay, so what I'm going to do here is I'm going to subtract PX times X from both sides, x times x. So what does that give us? That gives us income, oh, excuse me, income minus px times x is equal to py times y. I'm just going to divide by py all through here. So the py's cancel. And then I'll be left with this. So now what I have is I have a form, I have a solution for y that's only in terms of prices and in terms of x. So what I'm going to do here is now I'm just going to plug this in for y back up here. Okay. So I'm just going to drag this back down. What I'll get px over py is equal to, and I'm just going to cross multiply by alpha over beta over here, just to make this a little bit easier on myself. And then now I'm going to plug in this expression in here for y. So what I'll get, remember that this is all over x, so what I'll get is I'll get, excuse me, I'll get I over py times x, and then I'll get minus px over py. Okay, so all I've done here is I've plugged in for y. Now what I'm going to do is I'm going to move px over py. I'm just going to add it to both sides, so then it gets canceled out here, and then I'll just have px over py over here. I can simplify a little bit, and then what I'll get is I'll get 1 plus beta over alpha times px over py equals I py over x. Okay, so we're starting to see how a solution for x can come about. So let's quickly get there. So if I multiply py on both sides, then notice that py's cancel out in 2 places, so that's good. And then what I'm going to do is well, let's see. I'll multiply by x on both sides and divide by 1 plus beta over alpha px on both sides. So what I'll get x equals I over beta plus alpha times px. Okay. Okay. Or if I want to simplify that, what I can do is notice. Excuse me. Hold on. Let me note that if I want to simplify 1 plus beta over alpha, then if I multiply 1 by alpha over alpha is just 1, so it's the same thing, then I get alpha plus beta over alpha. Okay? And so alpha plus beta, so here, I need to clean stuff up. So let's make a little bit more room. Sorry about all this. Okay, so now let's just recap. So x is equal to I over alpha plus beta over alpha times px. And then notice that I can just rewrite this with alpha over alpha plus beta I over px. Okay, so how do we get back to y? Well, one way to notice this is to notice, and this is going to be the simplest way to do it, is to notice that if we multiply by px on both sides, this expression gives us px times x is equal to alpha plus alpha over beta times I. Okay, and so the left-hand term, the price of x is the price of x times x. So this is going to be expenditures on x. X. This is going to be a term that's going to be less than 1 by definition. And so this is essentially saying this is the share of income that I'm going to spend on X. So if this is expenditures and this is my income, I, then this term here is going to be the share of expenditures that I'm going to spend on X. So if this is less than 1, then we must spend the remaining share of expenditures on PY. So expenditures on Y are going to be PY times Y. And so those must take up the remainder, beta alpha plus beta times I. And to see that these shares add up to 1, you can confirm that for yourself by just adding them together. You'll get alpha plus beta over alpha plus beta. Those cancel, and you just are left with 1. So we can't spend more than 100% of our income. So again, by sort of process of elimination, the remaining expenditures on Y must have this form. Okay. So that gives us a general form for what expenditures on X and Y must look like. So I'll clear this and let's go through what the slides have to say about this. Okay, so again, we want to use the utility maximization rule. What we did there is we equate the marginal ratio of substitution to the relative slope of the prices. And again, the reason why we're doing that is because we want to make sure that the marginal utility of each good per dollar spent on each good is equal. Otherwise, we'd be better off consuming different shares of X and Y, as I said earlier. So if we rearrange, we can write Y in terms of X. And then what we can do is we can use the budget constraint to plug in, and this does it a little bit differently than I did it. We can just plug in for Y in terms of X in the budget constraint, but regardless, we still get the same optimal X. And we can either do the trick that I used, or we can just do the same to get the optimal Y star, and that's going to give us those two general solutions. And one thing to note is that alpha plus beta will frequently equal 1. This is going to be the case for almost all of the course. And so the general solutions become a lot simpler. They just become that X star is equal to alpha times income over the price of X, and Y star, the optimal consumption of Y, is just going to be equal to beta times I over PY. And the intuition then, in that case, becomes even simpler. X times PX, remember that's just expenditures on X. That's how much the consumer spends in total on X, is just equal to alpha times income. So what does that mean that alpha is? Alpha represents the share of income spent on X. Likewise, we can just rewrite this right-hand side to show us that beta is the share of income spent on Y. And so I'd say that you need to memorize these, but really you don't have to memorize that X is equal to alpha times I over PX. What you should just recall is that if we go back, note that Y is just the exponent, or sorry, alpha is the exponent on X, and beta is the exponent on Y here. That's what this utility function is telling us. And so we can just look at that utility function and say, well, it looks like we spend alpha percent of our income on good X and beta percent of our income on good Y. And so that's what these general solutions are telling here. So that's the intuition that I'd take away from this general solution, is that in Cobb-Douglas utility, we know how much the fraction of our income is spent on each good just by looking at the magnitude of the exponents and what goods they're associated with. And so this slide just spells out in writing what I just said. Okay, so exercise 4 wants us to go back to our example on utility maximization, where we had that the utility of apples and oranges was just given by apples to the 2/3 and oranges to the 1/3, and that we assume the prices and income are the same. Where, if I recall correctly, income was 60, the price of apples was 4, and the price of oranges was 2. Okay, well, what do we know about apples here? Well, there's 2/3 in the exponent for apples associated with apples. So that's going to mean that we spend 2/3 of our income on apples. So this is, again, expenditures of apples. And so if I plug in here for the price of apples, here that's 4 apples, and then I have 2/3 times 60. Well, the right-hand side is just 40. And so if I divide both sides by 4, I get that apples is equal to 10. Likewise, let's, we know that from a previous exercise that we optimally consume the same number of apples and oranges. So you could just say we're done, but just for completeness, we also know that from the Cobb-Douglas general solution that we want to spend 1/3 of our income on oranges. So PO times O, or expenditures on oranges, is going to be equal to 1/3 of our income. Plugging in for the prices of oranges, we get 2 times the number of oranges consumed, equal to 1/3 times 60. 1/3 of 60 is 20, and then we have 2 times oranges. So the optimal number of oranges is just going to be 10. So that confirms that the general solution of the Cobb-Douglas utility function gives us the exact same solution as equating the marginal ratio of substitution to the relative prices of apples and oranges, as we did before. Of course, the general solution has all of that baked into it. In order to find the general solution, we just equated the marginal ratio of substitution to the relative prices. But this is a much simpler way, where without equating any of the marginal ratios of substitution to the relative prices, we just know that we can get to the solution based on that math, because the exponents are telling us what the share of income is spent on. So that's a really quick way, without to do all of the math. I really highly encourage you to memorize that, or at least keep the intuition in the back of your mind, because otherwise you'll have to be, in order to solve a lot of things in this class, you'll have to equate relative prices to relative marginal utilities, and that takes a lot more work, and I advise you not to do that. So that's all I have for this section. Dennis will take over next week, and I hope to see you all in my office hours on Tuesday this week. So thank you so much, and see you 2 weeks.